All right, we're here for AP Physics Work Kinetic Energy Theorem. On to 2 here. I'm going to do problem 3. All right, I swear, the rest, these next few problems, these will go a lot faster than problems 1 and 2 did, okay? Here we go, problem 3. An archer pulls her bowstring back 0.4 meters by exerting a force that increases from 0 up to 230 newtons, okay? So that's like, assuming that she's pulling it nice and smoothly back, so we're not changing the kinetic energy of the string. We're just going kind of nice, kind of speed. Anyway, what's the equivalent spring constant of the bow? So here we go. So let's see here. We have this bow. I wish I had a brown marker. It doesn't look like wood. But anyway, here we go. All right. Does that look right to you? Yeah, sure, why not? Okay, anyway, right. Okay, we got our arrow, right? Nice arrowhead, Dave. Okay, anyway, there we go. Okay, anyway, right. And the point is that, let's see here, give that arrow some fletchings, right? Right, there we go. Okay, anyway, so that bowstring, right, starts off like this, right? And we're going to pull it back, right, through 0.4 meters, and it's going to be pulling back on us. So here we go. So we know that if I went ahead and I did a graph of that force versus position, you say as I stretch that bow, right, stretch that back, the bow is bending. We're going to treat this like a spring. We're going to end up with something that looks like this, right? If I pull in the left direction, it pulls back in the right direction, sort of thing. So if my position is positive, the force is negative, sort of idea. I don't know. I guess I'm calling that the positive direction. Anyway, so I'm getting this graph that looks like this. And so we remember that this is like the equation for Hooke's law spring. F is negative kx, right? And so they tell me that my force is increasing uniformly, so nice and linearly from 0 to 230 newtons. And so that slope is my spring constant. And so this is as I go from x is 0 to x equals 0.4 meters. Good enough. We recognize that slope is going to be at, so you say, hey, this is just rise over run, 230 newtons over 0.4. Punch that in my calculator. Why not? Should be able to do that one in my head. That's okay. 575 newtons per meter. That is my effective spring constant for that bow. All right. Okay, moving on. Let's go to part B. How much work is done by the archer in pulling back the bowstring? You say, well, work is that area under my force position graph, right? This is like the work done by the bowstring pulling against us. Flip the sign, it'll be the work that I did. You know what I mean? That she did, sorry, the archer did as she pulled back the string. So basically, it's just gonna be that area. You say, hey, that's a triangle. You say, hey, wouldn't the area of that triangle be like 1/2 base times height? So this is my work for part B here. Sorry, I should probably be doing it down here. Wouldn't that area is the work 1/2 base times height? That'll be 1/2. The base is that x, the distance we stretched it, and the height is that 230. Right? I'm flipping the sign because I want the work that I put into the bow, not how hard the bow pulled against me. And so you say, well, if I do that, then you say, hey, the x that was 0.4, half of 0.4 times 230, and you say, hey, that's going to be, well, it's just going to be half of what I, whatever, 0.5 times 0.4 times 230. You say that's going to be 46 joules. Okay, so that's the work that I did, that she did, pulling the bowstring back. Which takes me to part C. If, when I release the bow, right, it's going to shove, that bowstring shoves on the arrow, right? And they're asking, if all of the energy was transferred to the 0.05 kilogram arrow, find the velocity of the arrow when launched. Now, in fact, will all of that energy stored up get transferred to the arrow? Well, no. You know what happens if you fire a bow, right? If you fire that arrow. When I left, I go, and it goes twang, and that bowstring's going. Blah, 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 blah. There's clearly some energy left in the bowstring. It didn't all get transferred to the arrow, but the bulk of it probably did. We're going to go ahead and just presume that we'll just approximate and say all the energy got transferred to the arrow. So the energy that I stored up, it's going backwards again. That bow is going to do that same amount of work. It's going to give 46 joules of energy to the arrow, right? We'll be losing that energy, transferring it to the arrow. The arrow will be going, say, in this direction, and the force from the bow is going in that direction. We're going to be doing positive work, transferring that energy to the arrow, 46 joules. So that work done on the arrow is going to be equal to the change in the kinetic energy of the arrow. That's going to be that 46 joules, and that'll be equal to the, that's going to be, here, let me do one step first. Final minus initial, but since the starting velocity was 0 for the arrow, that initial kinetic energy term is going to drop out because V0 was 0. So I'm just going to have this 1/2 mass of the arrow times the final velocity squared. So that's going to be 1/2 the arrow's mass, they tell us, is 0.05 kilograms, and the final velocity squared. So I can solve for that in my calculator. Let's see here. 46 times 2 divided by 0.05, right? And then I'll take the square root of that. And that arrow will be going at a blistering final velocity of 42.9 meters per second. Okay, and that's problem 3. All right. Told you it'd be faster than the other 2 problems.